We're going to continue our discussion of optimization and finding maximum and minimums this week, but we're going to do so with constraints. And we kind of had a couple questions pop up with this in the homework this past week. But the idea is that we're going to try to employ three techniques. Well, first, there's the analog of the closed interval method. Yeah, and we kind of focused on that last time, so we're not going to explore that anymore. But the other two techniques, substitution and Lagrange multipliers, we're going to do both of those well, for this class, not necessarily today, but for this class. Substitution is something that sounds relatively straightforward, so might not need so much explanation, but we'll see about that. And then there's just Lagrange multipliers, which is a very interesting way of solving these problems. And so we're going to just dive right in with substitution. Okay, so here's a problem. Find the minimum and maxima of this function subject to that constraint. And so all we're going to do is really just substitute in that constraint into the function. But when we do that, there's different choices that we can make, right? So I could rearrange the constraint and solve for x squared. And I get that one. I can rearrange the constraint and solve for y squared, right? Or, since it is the unit circle, I can parameterize it too. So what do? And so right now I just want you to pause the video and attempt each of these methods individually and see what you get. Okay, well, if we happen to do this first one, I believe we should have gotten g of y is that after we substituted in, and then we look at find the critical points, we get y is equal to 0 as the critical point, then we do the second derivative, okay, we get local maxes, and then actually it's enough to say that we're at absolute max. Okay, you can do the compact region method to prove that. Okay, similarly for the second one, if we solve that one, we get an absolute minimum. Wait, what? They don't agree. This is interesting. But then if I parameterize, we get everything. We get the absolute mins and absolute maxes. Okay, so you're probably thinking, oh, I just parameterize, right? Well, you can, but these other two methods should work. So why did we get different things with the substitution? Okay, well, if I look at that, and here's my constraint, if I solve for y squared, right? So we would want to optimize this function, but remember that, so my constraint, again, I can visualize that just as the unit circle, right? So then if I do that, so here's my unit circle, okay, and so on this unit circle, right, I'm restricting that surface that I'm on, and we recognize that surface maybe as a saddle. And so if I kind of visualize this is the kind of image that I get, right? I have a saddle, but I'm restricting it just to be within that particular domain. So visually we can inspect it and say, okay, well, I should have two maxes and two mins, so why isn't my algebra matching up? Well, when I think about optimizing this function, I can, but I need to remember one important thing. I need to remember that, let's see here. Yep, I need to remember that, well, if I'm on the unit circle, x is particularly restricted. X is between -1 and 1, right? So then I can do this and I get, I can optimize this, and I remember I found that x is equal to 0. There's a minimum here, right? And then so with this, when I substitute this in, I get y is plus and minus 1, right? So I get minimum here, but then the maximum, according to my closed interval method, I'm just abbreviating here because I don't want to write that all out, the maximum would occur at the endpoints. So x is plus and minus 1, which, if I do that, give me that y is 0, and then I get all my I get all my critical points. Okay, so I can do this with substitution, but moral of the story is be careful, okay? All right. With substitution, you may need to consider endpoints as well.